Hi, so today we're going to talk about paging and segmentation. So paging is basically where we break up our logical memory into fixed size called pages, and then we're going to put those into physical memory. So we're going to have a page, then we're going to have a frame. It says page frame, but we'll mostly call it a frame. This is a fixed size block in physical memory. Page is a fixed size block in virtual or logical memory. And a page table is an array that keeps track of which pages of a given logical address reside in which page frames, because they might not necessarily be in order in physical memory, and so we need to keep track of where they are. So let's look at this visualization really quick. Here we have process P1. It has a logical address space. It has 3 pages. They're mapped to page frames 0, 1, and 6 in physical memory, as we see here. And then process 2 can also have pages, and here they're by the one in process 1. Process 1 and process 2 don't know about each other's pages, and that's fine. They just should know about their own pages. To keep track of the mapping, we're going to have a page table for each process. Each page table entry is going to then point to the frame. So we'll have an intermediate page table here, one for each process, so we'll have 2 of them. And so P2's page table is going to point the 2 frames holding pages 0 and 1. So let's answer these questions. For each process, are pages numbered consecutively starting with 0? Frames are numbered consecutively starting with 0? Frames are numbered consecutively starting with an integer n greater than equal to 0. Okay, so let's look up here. In pages, they're numbered consecutively within each process, and then the whole frame is numbered consecutively. Let's see what they want us to learn from this. So each process has a separate logical space, and so page numbers start with 0. Oh, for each process. Sorry, I didn't read that well. So yes, per process, the pages are numbered consecutively. The processes are put in different page frames, and so it doesn't have to start at 0. And then, yeah, the same thing here. Okay, the OS maintains a single page table for all processes, a separate page table for each logical space, or a separate page table for each physical space. So it's each logical space. In a logical space, each process has its own logical space. Okay, so here we have a whole paragraph that talks about how logical addresses are mapped to physical addresses. So what I'm going to do actually is just go through this visual, and then it'll be really more evident. Okay. So here we have logical address space, and this is just the example. So in this example, we have a 5-bit address. And that we have 5 bits here because apparently this computer is assigned to have an address space of 32 words. So if we remember, binary 2 to the 5th power is going to be, so we have 5 bits to the 5th power will give us 32 words. When the space is divided into pages of size 8, then 3 bits are needed for the offset. So the size of the page is going to be 8. So we're going to have 8 addresses within each page, which has the range 0 to 111. So this is going to be our offset within our page. This is going to be our page numbers. So this would, yeah. Okay, the remaining 2 bits of this address are going to be the page number. And because we have 2 bits here, this means we can have 4 pages. So depending on the way you divide this address space is going to be how many pages you have and the size of each page. The more pages you have, the smaller each page is. So if we had 3 bits, we'd have 8 pages, and then the size would be 4. Okay. If we had 1 bit here, then we would have only 2 pages, but each page would be bigger. It would be 16 words. So whoever's designing has to figure out how many pages and how many words in each page. This same address space can be divided differently. So here, what I was just talking about, if the page size is 4, then only 2 bits are needed for W. And then the remaining 3 bits could identify 8 different page numbers. So physical memory, it's divided into frames in a sense. So this is our virtual memory. This is the actual memory, in your computer. It's divided into frames in a similar manner. The frame size must be identical to the page size. So if you have like, like here, this is our size, our frames, our page size. This is how many words are on a page. This has to be the same. So then with a 6-bit physical address space, 16 frames are created, 2 to the 4, 16. Our physical memory is always going to be bigger than our virtual memory, or it should be, because our programs are going to be smaller, right? So we have much more physical memory, so we can fit several different processes into that memory. Then here they say if page 0 is mapped to frame 1, then P, this 0, is mapped to F. Okay? All logical addresses starting with 000 are then translated into physical address 0001. The offset's unchanged because the sizes are the same. And so if we're like at this part of this page, then we just go to this part of this frame. Similarly, if page 0 is mapped to frame 15, logical addresses starting with 011 are translated to physical addresses starting with 1111. And again, the offset within this frame would be the same. Okay, so the size of W, which is this offset part, determines the number of words per page. And the size of P is going to determine the number of pages. And then the size of F is going to determine the number of frames. So an address space with an address size of 16 bits and a page size of 512 words will consist of how many pages? So we have to figure out how many bits is 512. So let's see, let me think. 1, 2, 4, 16, 18, 1632, 64, 128, 256. So that's going to be 9. So we would have 9 bits for 512. So 16 minus 9 is going to give us 7. Yeah, there we go. Okay. Okay, so address translation. So with paging, we're going to have a logical address that's broken into 2 parts, a page number and an offset. Similarly, a physical address is broken in, so that's a logical address. It's got a page and an offset within the page. And then a physical address is broken into 2 components, a frame number and an offset. And these are the notations, PW and FW. So here they give an example. If P is 4 bits and W is 5 bits, then 2, 6 denotes the 9-bit address, which is the concatenation of the 2 components, 2 and 6 in binary. So let's look at this visualization here. It's very nice. Okay, so we have a logical address. This is a page number and then the offset. Remember, they're not showing this, but we have a page table that's going to tell us which page number goes to which frame. Well, now they are, so the page number P is used to access the page table. We have this index P that's going to tell us where to go. And then we're going to have the frame number in here, and that will map it, tell us which frame to go to. Okay, so we've got the F there. And then we have an offset. It's copied from the logical address to the physical, and that doesn't change because we're just figuring out which frame now we need. And then FW is going to identify the word in physical, because that's our offset within that frame, corresponding to the word in the logical address space at address PW. Okay, so let's look at this. So an address 4-bit offset. Okay. So the number of pages is going to be 2 to the 5th power. And the size is going to be 2 to the 4th power. And then the address 2-3. So let's find 2 and 3. So this should be it. Oops. Oh, forgot my binary for a minute. 2, that's 1. Sorry. Because it's 5-bit. So excuse me for that. I forgot our 5 and 4. So 2 is a 5-bit binary number is 00010. 3 is a 4-bit binary number is 0011. So we have to remember that. Which size? Because I was just seeing like I was basically dividing it in a weird way. So we're going to divide it into 5 and 4. So we have 4 here and then 5 here. So that is 2. Okay. And then if the logical address 3.5 is mapped to the physical address 4.5, then the page table entry at offset 3 is 5. The page table entry at offset 4 is 3. Or the page table entry at offset 3 is 4. So this is our page, and this is our offsets. But they call this offset 2 because it's like an index. I like to call it an index. They're kind of messing with their vocabulary. This is the page table. This is so let's try to figure out the page table entry at offset 3 is 4. Because we're basically going to go to index 3, and that's going to tell us frame 4 is where we should be looking for this page in memory. With the above mapping, the starting physical address of the frame is, it's going to be so the offset, the start would be at 0, and then 5 would be the offset